Hello, my name is Chris Wilson. I'm the Technical Director of Unity Titanium, and I would like to present my presentation on the revision of grade 12 titanium within the NACE MRO 175 ISO 15156-3 standard for sour gas service. The background, the International Titanium Association has sponsored this project, and the goal was to remove restrictions on grade 12 titanium within the NACE MRO 175 ISO 15156-3 standard. The current standard has the following restrictions on hardness and annealing. UNS R53400, which is grade 12, shall be in the annealed condition. Heat treatment shall be annealing at 774 degrees C for 2 hours, followed by air cooling. Maximum hardness shall be 92 HRB. So the restrictions there are that the annealing requirement requires a batch annealing furnace. So continuous annealing product is currently not permitted by that statement. Also, the hardness values greater than 92 HRB are not being permitted. There was some thought that that was too low of a hardness for grade 12 with the increased tensile and yield strength, and that really the hardness didn't have a real effect on the corrosion properties for these titanium alloys. So the revised wording that the project was undertaking was basically to remove the entire current wording requirements and streamline that. The new wording will be UNS R53400 shall be in the annealed condition. As you can see, there are no heat treatment requirements, no specifications on a specific annealing cycle, and no requirement for hardness. The ballot status, the current ballot status has passed all of the requirements within the NACE standard and the NACE task groups, passed voting within the maintenance panel, the TG 299 task group, and the MRO 175 ISO 15156 maintenance panel. Right now, however, we are timing was not good. They are in the middle of a new revision to the standard, a 2020 revision. So we are waiting for that new revision to come out. Once that new revision comes out, the grade 12 changes will be implemented on the next available technical circular. Unfortunately, just timing and the way these international standards work, they are not easy to make any modifications or any changes, as anyone would tell you. And they tend to take a lot longer than you think they will. We're hoping that the balloting, as I understand it, for the new standard is complete. Believe that will come out this very shortly now. So we're hoping the first technical circular will be sometime early next year. Just to review the table from within the MRO 175 standard, this is the table A.41, which shows all of the different titanium alloys that are approved within the standard. I've highlighted here the R43400 footnote C. And as you'll see within this footnote C, it still has the same wording, same requirements. And that will be left in the standard. The reason for that is that we're grandfathering that footnote in there because there is currently a product and a supplier that is manufacturing in accordance to these requirements. And has been making a specific part for a specific application for years. So we did not want to remove that for that supplier's sake. So that was left in. And as an alternative, what we did was add a footnote I. And you can see that for the footnote I, there are now, any new grades that get added or modified, you have to have limitations on temperature, partial pressure, chlorine concentration, pH levels. And that's all based on the testing, the corrosion testing that was performed in order to get this added to the standard. So you can see, although we do have the restrictions, there are no restrictions on processing. So we do have the NACE level 7 limitations on temperature and H2 concentration. But if you look at the footnote I, UNSR 53400 shall be in the annealed condition. So the restrictions on how to anneal the material and also the restrictions on hardness have been removed. So what does this mean? Removing the barriers for grade 12 titanium producers is the key here. We've removed restrictions on the annealing cycle. There are no maximum hardness requirements, and we've increased supply availability for the NACE MR0175 sour service market. So there's going to be more people that can participate. The other advantages of just grade 12 in general is the fact that it will have improved mechanical properties, improved corrosion resistance, and potential project cost savings over the standard grade 2/2H titanium grades. I'd like to review some of the corrosion advantages. On this slide, you can see the crevice corrosion chart that many of you are probably familiar with for titanium alloys. This is crevice corrosion in saturated sodium chloride brines. As you can see, there are different lines for the different grades of titanium. The standard available grade 2, grade 1, grade 2H. Anywhere above this line, if the pH is more basic, you will result in no hydrogen pickup, no corrosion. However, if you fall below that purple line, then you will see that, there's a potential for crevice corrosion below the grade lines. So if you're in a more acidic environment at a higher temperature, grade 12 may be an option for you. Down around pH levels of 3 and above, grade 12 could be a viable alternative. If the pH levels are even lower than that, pH level 1, then there would be the availability of grade 7, grade 7H palladium grades that would be able to handle that environment. I did not include the ruthenium grades on this chart, just simply because the availability in the market is not prevalent. Mechanical property advantages. So this table here is the chemistry table. It's just showing all of the approved titanium grades in the NACE standard. Grade 1, grade 2, grade 12. And then we get into the grade 25, which is the Ti 6,4 palladium with addition of palladium and nickel. Grade 28 is Ti 3,2.5 with the addition of ruthenium. Grade 29 is the 6,4 with the addition of ruthenium. And then we get into grade 19 and Ti 6,246. Excuse me. Okay, so looking at the mechanical properties of those grades and sorting them by increased tensile strength. Now the mechanical properties are coming from ASME SB 265. There are really no specific mechanical properties within the NACE standard. But if you look at the ASME standard and sort them by tensile strength, you can see the green rows, the grade 12, falls sort of in the middle of the pack. Obviously not as high of a tensile strength or high properties as the alloyed grades, but a significant improvement over mechanical properties of the grade 2/grade 2H. Took that same data and just threw it on a chart for visual representation, and you can see that grade 12 here is right in the middle of the pack. Again, much better than grade 2, better than grade 2H as far as increased tensile strength. Not as good as some of the, or not as high as some of the other alloy grades. And that data is right from the ASME SB 265 standard. Now, looking at which grades are approved within the NACE standard, and then also approved within ASME Section 8 Division 1 code, you can see that 4 out of the 8 grades are approved titanium grades within the ASME Section 8 code. Those being grade 1, grade 2/2H, grade 12, and grade 28 with the Ti 3.2.5 with ruthenium. Now, when we look at those, just on a allowable stress at elevated temperature and chart those out by temperature, you can see that grade 12 has a significant improvement over the routinely available grade 2 grades. The gap in the stress for grade 12, there's, if we're looking at a grade 2 delta, there's a 5.8 KSI average. That's a 62.5% increase at 400 degrees Fahrenheit. Versus grade 4, it's not quite as high, it's 4.2 KSI average, but that's still 36.9% increase at 400 degrees Fahrenheit. So the implication there being, by going to a stronger material, higher tensile strength material, you will be able to reduce the wall thickness in a pressure vessel application, thus saving you money on material costs. Cost factors. Okay, so this is a rather lengthy equation, but I wanted to throw it out there just to have it on record. It's a good, I believe it's a good tool to use when you're designing a project, to looking at and comparing material costs. So what I did, you'll see on the next slide, is I looked at various alloys, looked at the, number one, the material alloy cost, which, just take that with a grain of salt. That's ever changing, and it's probably something you would want to do, when you're looking at a project, and have to do that routinely because prices are always changing. Then looking at the density, thickness, and comparing the grade 12 design allowable at the temperature versus whatever the materials design allowable is, and then normalizing that against the cost of grade 12. In this case that I'll show you, we're looking at plate with a thickness of 1/4 inch. So the pricing is based on 1/4 inch plate. And again, I'll show you this, but take it, it's something that you would want to do on your own. Okay, so here's the chart. We looked at some various competitive alloys. I did not include the grade 28 just due to lack of market data and lack of availability. So that was not included in here. If you look at the orange line, that is our standard grade 2H. The blue line is the normalized grade 12 that becomes the standard in this example. So it's normalized at 1 across the board at every temperature. And then we chart the various grades at the elevated temperatures, giving the ASME design allowable properties. So if we look at grade 2, one thing to note is that in all cases at every temperature, this breakdown is showing that grade 12 has an advantage over grade 2, which is something that I think surprised some people. So that's something definitely to consider. It's definitely competitive against titanium grade 2. Now, when we look at some of the stainless and other materials, 316L, 2205, obviously if those materials work for the application, then they have a significant advantage over grade 12. So that's the direction you would want to go there. Now, some of the other alloys, C276 and 625, you can see it changes as the temperature increases. Those materials become more competitive. But at lower temperatures, depending on the application, if the temperatures were 400 degrees and below, then grade 12 is certainly competitive, in some cases more competitive from a cost factor aspect. So now I'm going to sort of go away from the grade 12. There are certain instances when grade 12 is not sufficient from a corrosion, maybe a crevice corrosion aspect, and you may need to look into palladium grades. So I wanted to talk about some cost considerations with increasing price levels of the palladium alloy, or the palladium in general. As you can see here, that's the same chart I was showing earlier. Grade 7 palladium bearing alloys are the standard choice when grade 2 and 12 are susceptible to attack in hot reducing, oxidizing acidic halide media. So you can see, depending on, what the environment is, you may need to go to a grade 7 or a palladium bearing grade. Now, when you look at it, the cost of the grade 7 with the palladium added is significant. It's estimated greater than 7 times compared to grade 2 and grade 12. So there are lean palladium grades, and that's what I wanted to discuss, the grade 16 and 17, that may be a viable option. So at this time, with the palladium prices going up, it's something that should be considered. This is a chart, just have the reference down there. You can go out and look at this, but just wanted to show, what's been happening in the palladium market in the last 2 years, 2.5 years. Since the beginning of 2018, palladium price has more than doubled since 2018. So it's really significant. Cost has really gone up, and as a result, availability has also become an issue. But when we were down around, palladium's always been expensive, ranging from $800 to $1,000 for the past 10 years, but now we're up around the $2,200 range per ounce. So what are the requirements? Grade 7, the chemistry difference is between standard grade 7, grade 11, the palladium range is 0.12 to 0.25%. Now, the lean palladium grades, grade 16 and 17, the required range is 0.04 to 0.08%. So that's basically 3 times less the amount of palladium is required in the lean palladium grades. Now, why is that? The lean palladium grades, contents of grade 7 is reduced from 0.18 to 0.06 versus the lean palladium grades. That's based on the specification range midpoint. The lower palladium content can reduce costs by 20 to 35% depending on the product. Corrosion performance of the palladium grades is not significantly reduced when compared to grade 7. So I'm going to show you that chart here. So this chart is showing corrosion rate in millimeters per year of grade 2, grade 12, grade 16, and grade 7. And this is in boiling hydrochloric acid, various weight percentages. And as you can see, grade 16 is showing significant improvement over grade 12 and grade 2, and not that far off of grade 7. It's very similar. So, in most cases, or in many cases, I should say, grade 16 would be sufficient. So it's, again, one of those things that you should really consider looking into. If grade 16 is sufficient for your application, then the cost of that grade is significantly lower than the grade 7 and should be something that you would consider. Okay, that's all I had on the palladium grades. And just in general, just give you a summary. The grade 12 modifications will be included in the first technical circular publication of the revised NACE MRO 175 ISO 15156 2020 standard. We believe that'll come out at the end of this year. So the first technical circular we're hoping will be early next year. Key benefits, again, removes the barriers for grade 12 titanium producers, no restrictions on annealing cycle, no maximum hardness requirement, and increased availability. Also improved mechanical properties, corrosion resistance, and potential project cost savings over grade 2/2H. So again, grade 12 is a viable and competitive option when all factors of the project and scope are considered, such as allowable stress at elevated temperature, density of material, cost of material, and corrosion resistance. I'd like to thank you for sitting through this presentation. My contact information is there. Feel free to email me if you have any questions in regard to this information, or if you would like any other information. I'd be glad to help. Thank you.